you're going to put that away and turn it in with your note card at the end of class. If one of these two sees a green sheet in the rest of the class, don't fold it. You're not folding it. Don't fold it. Put it away. If one of us sees a green sheet sometime during class, you're turning it in then, okay? Don't do that. So at the end of class, when you come and bring your cards down, you'll also bring your quiz down. Okay, so if you can do that quietly, I can make some announcements. The first one is, so you're gonna, if you haven't realized already, you may learn very quickly that you're gonna need a lot of support in this class. And we have lots of opportunities for support, okay? Office hours, right here on Blackboard, there's an office hours link, and it lists all four of us. You are all welcome to visit any one of these 4 office hours, okay? So Annie and Kirk are the ones who are here with us to lecture. Some of you have Roy, and then of course myself. So please, you are all welcome to take advantage and come to any one of our office hours. You're going to need to do that in this course. Okay. Even if you felt like a whiz in math in the past, you may need more extra support than you thought. Okay? So just want to make sure that you do that. And then the videos. Okay? The way I suggest that you use the videos is, as soon as you can, after class, watch it and maybe make a nice formal set of notes out of it. Okay? Because, I think I've said this before, you could walk out of here and say, I've pretty much got that, 80, 90%, I've got it. But if it's the first time you've learned something, or the first time you thought about it in a certain way, with all the other things going on in your life, after 4 hours, after 6 hours, after 12 hours, it's going to fade. It's going to fade. So as soon as you can review it and reinforce it, the better. Okay? So that's how I recommend you use the videos. Don't wait till the night before the test to start reviewing the videos. Watch them as soon as you can after class. And I will try to get these. I had a delay on Wednesday, but these should be up by 5 p.m. the day of class. So that evening, they should be available to you. That might not always be the case, but I'll do my best. Okay. So let's. What are we doing here? I'm going to show you. Here's a photo of an SUV moving through a 10-foot wide crosswalk. The first question, why is the SUV captured in the photo as a blur? Why is it captured in the photo as a blur? But this is moving, okay, it's moving, but when you take a photo of something moving, why do you get a blur? Yes, sir? Relativity. Say it again? He said shutter time. What is shutter time? Yeah, so.
Well, the exposure on the amount of time these cameras exposure is open.
Right, so when you take a picture, the shutter opens for some amount of time, some finite amount of time. That's called the shutter speed. Okay? I think for this one, it's something like 1/40th of a second, or something like that. So some fraction of a second, the shutter was open. And so for that duration of time, light is coming into the camera. So something that's moving, then that image will come into the camera in all the locations that it was when the shutter was open. Does that make sense? Okay, so we've got this blur because it's moving through the crosswalk. So second question, devise a plan to determine how many feet the SUV traveled while the camera shutter was open. So can you devise a plan to determine how many feet the SUV traveled while the camera shutter was open? So I want you to think about this and maybe have a discussion with the person next to you. See if you can come up with a way to figure out how far did it move, or how long is the blur? How long is the blur? Go. will have made very little progress. Okay, here's a hint. Use tools and reasoning we've learned so far. Use tools and reasoning we've learned so far. Go. Okay. So I've added a little bit to the picture here. So anyone think that they can use tools and reasoning so far to
Measure the blur and the part where you can determine the two ends of it and then compare it to the crosswalk.
Okay. So she said measure the blur where you can see the two ends of it and compare it to the crosswalk. Other comments or additions or differences? Yes, ma'am?
I thought about how you could use the two bars and you have one since it says the crosswalk is 10 feet wide.
Okay.
One for the crosswalk. And then I couldn't remember what you said the shutter speed example was.
Okay.
Maybe make the other bar the shutter speed and kind of measure it.
All right.
But
So how what I drew right here, this white thing, can that play into your strategy? What could that be?
The length the car travels.
Okay.
It could be a chunk of the length of the sidewalk.
Chunk of the length of the sidewalk. Yes, sir.
It'd be from that blur point, like the back end of the wheels, how far that travel from that shutter.
Okay, so I was picking off, do you see there's this white dot here, right there? I was picking that off. So what did I draw? I draw a bar, right? I drew a bar. And what does that bar represent? Distance the car traveled. So now how am I going to get what that distance is in terms of feet? Compare it to the crosswalk. So what do I need? All right, another bar, like down here, like this?
It has to be where the bottom of the wheel is.
In the same plane as the car, right? So I'll have another bar like this. All right, how about here? So what if I use a bar down here like that? Will give us the right, will it be right? Like,
It's still 10 feet long.
still 10 feet long. He's saying it's still 10 feet long from here to here. Yes, sir.
The face where the car is, that's a lot, like, it's not the same.
Oh, please say it. Please say it. It's not the same. Someone.
why is it the same scale? It's a lot closer. It's gonna look bigger.
This is the big principle we've been talking about. Why does the bar matter? What's that? Not scaled correctly. What's that?
It's not the same relative length.
Relative length, relative size, relative size. What is the size of the blur relative to this bar? Is it the same as the size of the blur relative to this one? No, this is a smaller relative size to that longer bar. So if I use this one, I'm going to get a different number of feet as if I use this one. Right? We got it. So the reason it matters where I do this is because this is all about relative size. I'm going to use relative size to measure that length. And if I use this one down here as my 10 feet, then will my length be too small or too great? If I use this one? No, it'll be too small. The length of the blur relative to this down here is smaller than the relative size of that to what we actually need, where it's 10 feet. Does it make sense? I mean, it's 10 feet here too, but using the picture, we can't use that one. We got to use this one. So what do you guess the relative size is? Some people are saying 1/5. 1/5? So just as an estimation, how many feet did the car travel? 2 feet. 1/5. And so if it's 1/5 of the length of 10 feet, then you think it traveled 2 feet. Okay, so this is kind of a warm-up for what you'll have in recitation starting today and then also next week. I guess there's no Monday recitation, so we'll just have to figure out when you guys can do that activity. Okay, any questions on that? See how the bars and relative size can help us answer the question. Cool. All right, so I got a graph here. And so when you look at that graph, what are you looking at? What are you looking at when you look at that graph? Some people are saying points, right? So this is collection of points. Now I'm going to tell you that these quantities here, this x quantity here is time. And this y quantity is distance. What do you think about how I define those quantities, x and y, or those variables? I define them as quantities. The x variable I define as the quantity time, and the y variable I define as the quantity distance. What do you think about that? Okay? Good? No, why not?
It's missing a sort of scale, I guess, or what is it called? Yeah, units.
Okay, missing units. Okay, so I'm going to say time,
Yeah,
time in seconds,
great punch.
distance in meters. How about now? How'd I do? So now are we done?
No.
Well, people are saying no. What's missing? Christian.
From what point? Like time since what and distance from what?
Right. So we need to be specific. We need to be descriptive. So this is very descriptive. And with time and distance, we need a starting reference point. So this is time in seconds. Okay, so time in seconds since the ride began. Since the start of the ride. Okay, time in seconds since the start of the ride. And then the distance in meters between you and your friend. Riding in different cars. Okay, so I'm going to pick a point here. Did I just add a point to the graph? Did I just add a point to the graph? No, I just highlighted. I just picked out a point. Pick one out. Okay. So what's the meaning of this point? What's the meaning of this point? Distance between me and my friend at a specific time. Right. So if we can kind of estimate, what is that? Looks like 0.5 and maybe 1.55 or something. We'll call it 1.6. So that point is two pieces of information taken together. It's the correspondence of time since the ride started and the distance between you and your friend in meters at that time. Okay, and so all the points, each point on here is a correspondence of that time quantity and that distance quantity. That's just a little overview of graphs, what we talked about before. Okay. So, looking at this here, we've got the blue quantity and the red quantity. That's just how we'll kind of Same. The blue quantity, the red quantity. So what's the relative size of the blue quantity with respect to the red quantity? What's the relative size of the blue quantity with respect to the red quantity? Everyone think to yourself? And what would you say? What would you say? The relative size of the blue quantity with respect to the red quantity?
Red quantity is a third or maybe just a little bit more than a third of the blue.
Okay, so he said a third. We want the relative size of the blue quantity with respect to the red quantity. A third? Someone in the back. What do you think? Right there.
Say a little more than 2.
A little more than 2. A little more than 2. Well, those are a big difference. So is it about a third or a little more than 2?
We're looking at respect to for the blue from the red, and you're looking for you're gonna be more in that range of 2. It's not a third of the size, it's double up.
Yes. Right, we're measuring or we're looking at the blue with respect to the red. So it's going to be 2 and something, right? 2.1 or 2.2. Okay? So then I'm going to double the length of the red bar. So think to yourself, what's going to happen when I double the length of the red bar? Got it? Here we go. What happened? Did it do what you thought? Oh. So, based on what you're seeing between the relationship between the blue bar and the red bar, talk to the person next to you about relative size. Okay, so let me ask this. What's the relative size of the blue bar with respect to the red bar now? 0.8. You should be thinking 0.7, 0.8, something like that, right? Okay? So what's going on here in this relationship? What happened to the relative size? It changed, right? So every relationship we've focused on, looked at so far, what happened to the relative size when we changed the value of one of the quantities? Stayed the same. We always have been looking at relationships that maintained relative size. This one is not, okay? This one is not. So what I want you to do is, I'm going to play this. Okay. So if you were to graph the blue quantity as in terms of or as a function of the red quantity, could you make the graph? Could you make the graph? So, in that animation on the left, where are you looking? Where should you be looking to see what the graph would be like? Where are you looking? Top of the blue bar, because we have the red quantity, right, is represented horizontally so far, and then from there, the blue quantity, its height, or the length of that blue bar, will give us the corresponding y quantity. So remember we said let's put the plane on. And let's track where it goes, right? Turn the vapor trail on. So what we're getting at here is how the bar diagrams are just another way to show the relationship between two quantities. Okay, so you've seen lots of these in your life. Okay, and so these bar diagrams basically are just another way to show it. If you take the bar diagram and take that top bar and plant it on the end of the other bar, and then focus on the top of that blue bar, then you have what you guys have always seen as a graph. Okay, and what is that? So that's a collection of points that emerge as the x quantity grows, right? So we could stop it at any point, maybe. And we're highlighting some point right there. A correspondence of, in this case, it's the time in seconds since the start of the ride, right? And the distance between you and your friends. Okay, question?
So you can see more specifically the point. Is there any way to like get rid of the plane and just do the paper trail so you can actually like see where the actual point is? The plane is kind of hidden out. Do you know what I mean?
No, I don't understand your question.
Okay, so is there any way just to like get the line to show us instead
Oh,
of
take the plane off?
yeah.
Sure.
Very cool.
It's not real fun like that.
Okay, so let's talk about something called covariation. I'll move it. Covariation. Actually, if you put this in, type this in Microsoft Word, it'll give you a red line underneath. Doesn't think it's a word, right? So, what do you suppose this term is referring to? How do our topics thus far in the class relate to it? And what does it have to do with calculus? This thing called covariation. So what do you suppose it's referring to? Yes, ma'am.
How two quantities are codependent on each other.
Okay.
They vary.
Yeah, so she said how two quantities are codependent on each other, how they vary. Exactly right. How two quantities change together. How two quantities change together. Okay? How do topics this far in the class relate to it? What does it have to do with calculus?
Relatively t in the past has always been two numbers depending on each other, whichever way they move.
Uh-huh.
And covariation, they still depend on each other, but they can vary between positive and negative.
Okay. Yeah, so what does that have to do with calculus?
You can see that calculus is all about the changing quantities.
Right.
How they relate.
Yeah. He said that I said calculus is all about the changing quantities and how they relate. So the answer is everything. It's what calculus is. It's about covariation. It's about modeling covariation of two quantities in the real world. Okay? So we can define it as how two quantities change together. So we looked at, this is kind of a review of where we've been. We looked at multiplication and division. These are the basics of changing quantities and measurement. So we've looked at all these aspects of multiplication and division. Okay, and then we've looked at some visual representations, right? The horizontal bars. As one bar changes, representing the value of a quantity, how does the other bar change? And then we saw a graph with horizontal and vertical coordinates, okay, which we can build by transforming a horizontal bar diagram. Okay, we transform the horizontal bar diagram. It builds a graph with horizontal vertical coordinates like you've been used to. So the next thing we've been starting to talk about is what about symbolic representation of covariation? So we've done a lot of visual. So symbolically, how do we represent covariation? Okay, and that's with function notation. Function notation. Okay, so here we go. The distance a motorcycle travels, so this is kind of an experiment, a little bit of an experiment. So a distance a motorcycle travels from an intersection in miles is a function of the time elapsed since leaving the intersection in minutes. How did I do defining the quantities here? How did I do? Is there any question about what I mean? Did I include units? These are well-defined quantities. So when you're doing your homework, this is what you should practice. Specificity and including units, okay? So what I want you to do right now, when you saw that, G parentheses 8.3 on parentheses, write down right now what came to mind when that appeared. Write down exactly what you thought. Write that down. Yeah, we're recording, yeah. Just to yourself, no talking, just write down. What did you think when you saw that? Okay, so it would be awesome to hear 5, 6, 7 of you say what you wrote, but we don't have time. So here are maybe some possibilities. G times 8.3. Okay? Kind of looks like that, right? Okay, that would be a very weak, like completely wrong concept of what we're talking about. Very weak because it doesn't even do it justice, right? Okay, so G is a function of 8.3. That's also, so that's, at least we're talking about function now, but that's very weak. Well, G is a function of 8.3. Okay? So, and then there may be other things. But you all may be in a different place in terms of how you see that. So we may all be coming from, like I said, a different place, a different vision of that. But here's our goal. We're all going to converge to this. That when we ever see that, we want to conceive that right there as three things taken in harmony. Three things taken in harmony. So when you see this, hopefully you can start moving towards seeing three things. 8.3 is the input, a number of minutes in this case, okay? Into a function whose name is g. That's the name of the function. And what's the third thing? And where is the output represented there? The whole thing, resulting in an output of g of 8.3, a number of miles in space. So wherever you're at, whatever you wrote down, we need to start taking a journey towards this conception of it. When you see function notation, you see these three things, kind of like an egg, kind of, right? It's three things, but it's one thing. Or a fork with three prongs. It's three things, one thing. That's the same thing here, okay? Okay, another example. A function is defined as f of x equals 3x squared plus 8x minus 17. Do it again. Do it again. What came to mind when the expression appeared? Write down exactly what you thought. Go. Okay, so how about this? Is the general meaning of f of 2 the same or different than the general meaning of g of 8.3 in the previous example? Same or different? I'm glad most of you are saying the same. The general meaning is the same. But I'm guessing lots of you wrote down something to do with calculating a value, a process, doing something. You saw the f of 2, you thought, I need to do something. I need to calculate an answer. Okay? But did you say that in the G of 8.3? No. Okay? But they're generally the same. Okay? What? 2 is the input, the value of some quantity, into a function whose name is f, resulting in an output of f of 2, the value of another quantity. Same thing. Okay, so here's a function we're going to build over the next month. Excited? Okay. How many times does function notation appear in this? You find it, so take a minute. You can work with the person next to you. How many times does function notation appear in this? Oh, yeah, that's a good point. Okay. How many people say more than one? It appears more than once. How about more than twice? More than 3 times? Still some here. More than 4 times? Ready? Here we go. Ready? There's 1. There's 2. There's 3. There's 4. 5 times. So I ask you then, what will serve you best to understand this function? What's going to serve you the best to understand this function? Hold on a second. 2 choices. To see these 5 function notations as calculating something, or as meaning an output quantity for a given input quantity. Hopefully, I've convinced you that this, seeing each one of those as an output for a given input, when you see that, not as, oh, it means for me to calculate something. All right? It means the output for a given input. That's going to serve you much better in understanding something complicated like this that's using function notation all over the place. You see? Okay. Questions, comments? Okay. So, let's see. Where's my... So my hope was to have some time to work on the worksheets that I asked you to print out. Okay. But we're going to just go to the cards. But do that quietly, and I want to talk about the homework over the weekend. So hold on a second. I'm going to talk to you before you start. So, okay, that's not. So I posted a document from which you printed out pages 3 and 4. Your homework for Wednesday now is basically going to be to read and complete that whole document. I think it's 6 pages, 1 through 6, okay? But I'm going to post a new version of it with some changes, okay? So whatever you printed out, you can discard those, and don't click that link. When I put Wednesday's homework up, it will have the correct link with the correct document for that. Was it section 3? Section 3 of Module 1, okay? So that Section 3 of Module 1, the entirety of that will be due Wednesday. Possibly something else. Read Blackboard very carefully. So we've got the drill down. So name,